Hello there. I'm going to take a little time to show you how we can use Laplace transforms to solve second order differential equations. This first formula hopefully looks familiar to you because we used it when we were solving first order differential equations with Laplace transforms. This second one now is utilized to transform y double prime. We use in its place s squared times L at y minus s times y at 0 minus y prime at 0. And a reminder here, of course, that y at 0 and y prime at 0 are the initial values of both y and y prime. Okay, so here's a first example. We have y double prime minus 2y prime plus y is e at t. The initial values are both 0. So if these values are 0, you can imagine substituting 0 here, here, and here in the formula. And that will reduce these such that they only have the first term. Like this, the transform of y prime will now be s times the transform of y. The transform of y double prime, s squared times the Laplace transform of y. So each now only will have the first term, as these terms will all be 0. Okay, we solve these just like we did the first order equations. And that is, we start by taking the transform of each and every term. Like this. The transform of y double prime minus 2 times the transform of y prime plus the transform of y is the transform of e at t. Now, in this spot here and this spot here, we will be substituting using the formulas. Right here, we will be transforming using our table. This, of course, is number 3 in the table. I hope you have your tables ready in front of you. This will be number 3 in the table, okay, with the value of a equal to -1. So we will now have this. Again, we replace here with s squared L at y. And after the coefficient of -2, we replace here with s times L at y. On the right, we've used number 3 in the transform table. Okay, I can show you that here. Okay, it was e to the t, so it becomes 1 over s minus 1. Okay, so that got us to this step. Now, L at y is removed as common, giving us this trinomial in the bracket, s squared minus 2s plus 1 being the coefficient here. We divide by the trinomial because we are trying to solve for y. So we begin by isolating L at y. Now this trinomial is factorable. You see it is product of 1, sum of -2. So the numbers are both -1, making the factors s minus 1, s minus 1, or in other words, s minus 1 all squared. So our new denominator is the cube of s minus 1. Where do we find this in the table? Number 12. So let's take a look at number 12. So we have the cube of s minus 1, which means we have n equal to 3 and a equal to -1. If n is 3, the numerator should be 2 factorial, which of course is the same as 2. we have just 1 here. If we want 2, we put 2 there, compensating with a factor of 1/2 out front. We now have this part being a perfect match to transform 12 with these values of n and a. And so it is time to finally write our answer. Y is, this will be the coefficient out front, and we get here t squared times e to the t. Okay, we're going to look at a second example now together as well. Okay, so here is example 2. Y double prime plus 2y is 2. The initial values are 0 and 3. So we can substitute into those first formulas for the transform of y double prime to begin with. And in doing so, we will get simply s squared L at y minus 3. And of course, that's a result of y at 0 being 0, so the middle term is not present in this formula. We actually will not be transforming y prime, so we'll only be needing this one formula. Okay, so let's begin. We're going to take the transform of each term, just like this, transform of each term. 2 is the coefficient here. To transform the number 2, you use number 1 in your transform table. The transform of the number 2 is 2 over s. In place of the transform of y double prime, we use these 2 terms here from our formula. So we now have this equation. We're trying to isolate L at y, so this term moves to the right side, and L at y will be common factored from these 2 terms. Okay, so you can see this term on the right, of course it is added, and here we have s squared plus 2 in the bracket. Okay, so what I'm going to do now is divide each of these terms by s squared plus 2. And that ends up looking like this. S times s squared plus 2 in this denominator. And here, of course, there was nothing but 1 underneath, so the denominator is s squared plus 2. Next, you would go to your transform table to find these. And I will direct you to numbers 7 and 6. In 7 and 6, this number right here would be a squared. A squared. And therefore, a becomes the square root of 2. So let's take a quick look at those 6 and 7 in the transform table. For number 7 in the transform table, if we have 2 here, then we should have 2 here. And for number 6 in the transform table, if we have 2 here, we should have the square root of 2 here. Okay, so again, in number 7, the numerator is exactly correct. If this is a squared, this is also a squared. But for number 6, we want not a 3 up top, but rather a square root of 2. So what do? We push the 3. We put the number we want here, which is square root 2. Therefore, we have to divide here by square root 2. The coefficient will now be 3 over root 2. While here, since we have a perfect match, the coefficient will be 1. So we go now to the final answer, which will be a function of t. We put y equals, using number 7, for this term, we get 1 minus cosine of square root 2 times t. And then after the coefficient of positive 3 over root 2, using number 6 on this term, we get the sine of square root 2 times t. Okay, so that was a couple of examples. I will do a couple more, but I think maybe in a second video. Okay, great, thanks.